Hello, let us discuss our paper Image-Based Roadmaps for Vision-Only Planning and Control of Robotic Manipulators. We aim to use natural visual features on the robot for planning collision-free paths in image space guided by adaptive visual servoing without using a robot model. We use the cited method to identify visual features as green key point vectors in image space. Moving the arm, we collect images and key points, forming a dataset. Key points in the gray area represent the collision-free configuration space for motion planning. We define our vision-only motion planning problem such that, given a collection of key points vector in image space and a start and a goal key point vector, we find an intermediate set of key points vector. And if an obstacle is introduced, we find an intermediate set of key points vector within the obstacle-free region. We solve this using a roadmap-based or probabilistic planner. Lacking knowledge of the robot configuration space, we build the initial roadmap using Euclidean distances between key point pairs in image space. We define another distance metric for the paper. We estimate joint displacement by multiplying velocity with the frame rate. We create dataset including key point vectors for 2 frames and the estimated displacement. A neural network is trained to predict joint displacement from key point vector pairs. For benchmarking, we create a roadmap using actual joint displacement between consecutive key point vector pairs. We check collisions by forming polygons between key point pairs. If they intersect obstacles or safety margins, the path is discarded, otherwise they form a collision-free path. Using lazy collision check with A* search, we only check for collisions when necessary. We ran path planning and adaptive vision-based control for different start-goal pairs for all roadmaps. Top row shows paths without collision check and bottom row with collision check. All roadmaps avoid obstacles, but paths differ. These experiments use a different start-goal pair and obstacle positions. Notably, both cases in image space, control fails to converge as the controller stops abruptly. To assess the robustness, we tested with multiple obstacles and a virtual real-life object. The image space planner failed to converge, colliding with the object. To test the need for a global planner, we added an artificial potential field controller in multi-obstacle scenarios, which failed due to local minima caused by opposing repulsive forces. Learned roadmaps achieve 100% success across all control scenarios, while image-based roadmaps are faster in successful runs but fail more often as obstacle complexity increases. Thank you.